Okay. Thank you. Good afternoon, everyone. Thank you very much for organizing committee for inviting us to give this talk. Unfortunately, my supervisor couldn't come, and I have to present my talk here. But thank you very much for inviting us. So what I'd like to present to you today is our recent work on quantum anomalous Hall insulators, especially in quasi one-dimensional limit and induced superconductivity. But before getting into the details, I'd like to acknowledge our collaborators in this project, namely Professor Kangel Wang and his group in UCLA provides us with the heterostructures, and Professor Campton Lowe's group at HKUST helps us with the theoretical support. And he's my supervisor, Professor Lords. So I'd like to, first of all, start by giving a brief background about our work, and then I will give some specifics of the materials and methods, and then I will share the results of the 2 experiments that we have done on this heterostructure, and I have some concluding remarks at the end. Okay, so some of the most important achievements, I think, in the last 2 or 3 decades in condensed matter physics is, I think, the completion of this Hall effect family picture, where we discovered all the quantum counterparts of the classical Hall effects. And you know, we learned a lot of physics from studying these quantum Hall systems. For instance, the quantum Hall effect, as you know, is the precise quantization of the Hall resistance at certain magnetic fields. And at the time, the question was whether one can achieve this quantized Hall resistance without the need for any external magnetic fields. And it came much later, only after the discovery of quantum spin Hall effect. So the quantum spin Hall effect has this, it was first discovered in mercury telluride quantum wells, and it has a time reversal symmetry which supports the existence of the helical edge states. And once they doped these mercury telluride quantum wells with magnetic impurities, they could break this time reversal symmetry to obtain only one channel of a chiral edge mode. And once you have this chiral edge state, you can achieve a quantized Hall resistance. But still, in that mercury telluride samples, they needed some magnetic field, some limited magnetic field to see that exact quantization. And only the ultimate quantum anomalous Hall effect with 0 magnetic field was discovered in chromium-doped bismuth telluride samples. So, and it was theoretically proposed that you can have a chiral topological superconductor by inducing superconductivity on the quantum anomalous Hall insulators. And by just normal S-wave superconductor, you can proximity induce the superconductivity and achieve a effective P-wave superconductor. And this topological superconductor, in theory, supports odd number of chiral Majorana modes, edge modes, and Majorana zero modes in vortices. As you can see here, the quantum anomalous Hall state supports chiral edge mode, which is an electronic mode, and you can mathematically decompose it into Majorana, 2 Majorana modes. And if you can achieve this chiral topological superconducting state, one of the degeneracy of this chiral edge mode is lifted, and you can have only one chiral Majorana edge mode. And so that was what we would like to utilize in our experiments, and what we'd like to realize at the end. And the material that we use for our case is the 6 quintuple layers of chromium-doped bismuth antimony telluride films that are MBE grown on gallium arsenide substrates. And the Fermi level in this recipe is exactly in the middle of the surface gap opened by the chromium doping. So they tune the bismuth to antimony doping ratio to achieve that and we have we deposit 200 nanometer thick niobium superconductor on top of this QAHI film. And you can see the standard Hall measurement of this sample, where there is this exact quantization. And the interesting point is that in this QAHI states, we have this characteristic zero conductance plateaus that happens because of an intermediate trivial insulating phase. That can also be seen in this longitudinal conductance measurement with this dip at the same magnetic field that corresponds to this Hall plateau, zero Hall plateau. So we, on this heterostructure, we prepared different point contacts in order to see this spectroscopic signature of these propagating Majorana modes. So this work has been already published in 2019. And this is the schematic of the device that we have prepared. So we first deposit gold at the edge of this heterostructure, and then we pattern this gold to be in a point contact limit by patterning it into strips of 200 to 500 nanometers. And also we attach normal contacts on the surface of superconductor. And once you have this, you can drive the system through different topological phases by switching the magnetization of the QAHI. And that's what we did. So we started, for instance, in this case, we started from minus 500 millitesla to plus 500 millitesla. Of course, all the data are taken at 15 millikelvin. So at 500 millitesla, the QAHI is fully magnetized, and it's in a normal QAHI state, quantum anomalous Hall state. Basically, it's somewhere here. And then as you increase the magnetic field and as you reach this magnetization reversal, you enter into a chiral superconducting state, and then your Andreev reflection spectra also changes from a deep structure into a plateau-like structure. And as you go further, you reach this trivial insulating state with a normal zero conductance. And as you go further, you again enter into a chiral superconducting state with only one Majorana mode, and then normal QAHI state. You can repeat this experiment, same experiment, by reversing the magnetic field, and you will traverse this trajectory, basically, and then the same exact features will be repeated. And so this same experimental observation is in a good match with the theoretical calculations based on the same point contact spectra. Now here you can see the band structure corresponding to this system with this magnetic field axis. As you can again drive the system through these different topological phases with changing the magnetic field. And the calculated spectra for the Andreev reflection can be seen here with the observed experimental data. So at QAHI quantum anomalous Hall state, you have two Majorana modes that are canceling each other's Andreev reflection. So you have a dip at zero bias and a peak at the gap. And then you have, when you enter into chiral superconducting region, you have only one Majorana mode, which gives you this plateau-like structure. And then when you reach the insulating state, you have only zero conductance. But as I said, it's been almost 3 years now that we have done that experiment, and most recently we have been interested in observing this Majorana zero mode, as we have heard a lot today. And now the motivation for that comes from these two papers that were published in 2018. Both of them are basically talking about using a quasi-one-dimensional quantum anomalous Hall system, which is what we have, and in proximity to a S-wave superconductor. And so the idea presented in the papers goes like this. So we have chiral edge states in our QAHI, and if you can shrink this, narrow down this QAHI into a width that is comparable with the chiral edge mode localization length, the two edge modes will be coupled into each other, and then they open a hybridization gap in the spectrum. So this one is the normal chiral edge mode with linear dispersion, and then this one is for the narrowed down quasi-one-dimensional limit. And if you can induce superconductivity on this helical channel that is formed after the gap opening, you basically enter into a topologically non-trivial state which is characterized by the NBDI here. It's a BDI class topological superconductor basically. And then, as you can see, the superconductivity opens this pairing gap, and if you can enter into this NBDI is equal to one region, the regime, then you have this Majorana zero mode in theory that are localized at the ends of this quasi one-dimensional system. And then you can reach that region by either tuning your chemical potential or the magnetic field, or both together. So experimental detection of this Majorana zero mode bound at the boundary can be done by attaching a macroscopic lead on the QAHI and then grounding the superconductor. So when an electronic mode, which is a chiral edge mode of QAHI, is reaching the boundary, it will be reflected as a whole, and then a Cooper pair will enter into the superconducting side. And the conductance through this boundary will be doubled, and as a result, the Andreev reflection, there will be a resonant Andreev reflection, and then you expect to see a 2e square over h quantized peak at zero bias. Okay, so in real life, we wanted to basically realize this system by patterning our two-dimensional QAHI superconductor samples by using FIB SEM dual beam system with focused ion beam system use accelerated gallium ions in our case. So you can see the typical SEM image from one of our nanoribbons. So we can make sure that all the layers of this nanoribbon is preserved by checking with the SEM from the side and comparing the heights. And this is a AFM scan cut from another study that we have been collaborating with. And here I'd like to highlight that the cross section of the nanoribbons are not rectangular, but the top layers usually have narrower width than the bottom layer. And this is a typical image of our device where we prepared this 82 nanometer nanoribbon at the edge of this, at the boundary of this QAHI and niobium layer, niobium area. And the device geometry for our experiments device setup is like this. So we send the current from a QAHI side by depositing gold, and then we measure the voltage from the inner contacts. A real life image of the device looks like this, and this is the toy model for the theoretical simulations that I will come later. So in the first devices that we measured, we have observed some zero bias anomalies, but they don't look pretty as pretty as the theory suggests, of course, and it's not as sharp or any kind of, it has all these structures to it with some shoulders and with a central peak basically, and we wanted to reproduce the theoretical result, of course, but it didn't succeed yet. So what we observe here is that we have a central peak, and then we have all the shoulders, and then we have this diminishing Andreev reflection signal as you go out of the niobium gap. And just naively considering that it's of superconducting origin, we wanted to fit this signal, the spectra that we observed, but you need at least 3 gap values for fitting this with normal standard BKT model. And all these gap values are interestingly below the niobium gap values, and so we attribute these structures to the central peaks to the Andreev-bound states found at this interface. And another thing to note is that these shoulders are smoothed out at some of our devices, and they are, and in some devices we prepared several nanoribbons in parallel to each other to increase our chance of obtaining some results. So also that contributes to the smoothing out of all these shoulders. And also we observe that the conductance is very much enhanced, and in the theoretical prediction, of course, you have 0 conductance and with a sharp 0 bias peak, but we don't observe that, and we think and we suspected that there is a bulk conduction going on inside, in addition to the helical channel that is going inside the superconducting side. So we wanted the same theory group to help us in simulating this, our device structure, by considering that the Fermi level is lying inside the bulk gaps, bulk bands. And they did, and what they also observe is this kind of structure with the peak and all these shoulders. When they consider that, for example, for this black curve, the Fermi level cuts 3 bands inside the bulk, and for the pink and blue curve, it only cuts 1, this helical channel. And this is our experimental observation, where we increase the out-of-plane magnetic field, and we also see that the central peak and the shoulders are changing with the magnetic field. So as we increase the magnetic field, these shoulders go away, and then we reach a stage where we only have a central 0 bias peak, and that also disappears at 4 Tesla. 4 Tesla is around the same, that's the critical field of the niobium in our system, usually. And so what we suspected is that the applied out-of-plane magnetic field is somehow driving the system from the bulk and into the gap region, and where there you obtain this 0 bias peak that is coming from the only bound Andreev states. So this is for the device, for the second device, and this is theoretical simulation with considering the Fermi level cutting 7 bands for this blue one, and it goes down, and here it only cuts 1, the helical channel. So that's what, for the device 2, it looks almost the same with the 7-band cutting Fermi level simulation. And then as we increase the field, we also get this a very broad kind of a 0 bias peak, and then it's diminishing as you increase the magnetic field. And this is for the third device. The same story repeats, but in this one we had 9 nanoribbons in parallel to each other, so we don't see these 2 sharp shoulders here, and only a broad peak. And then this is the evolution of the peak at higher magnetic fields. So it also vanishes, and it goes away at about 4 Tesla. How much time I have? 5 minutes. So I think I can summarize. To summarize, so we have prepared point contact devices at the quantum anomalous Hall insulator niobium heterostructures at the edge of these heterostructures to obtain the spectroscopic signatures of the propagating Majorana modes. And the experimental observation of ours matches well with the theoretical calculations. And afterwards, we did the Andreev reflection spectroscopy at the end of quasi-one-dimensional system of the same heterostructure. And we are still ongoing, these studies are still ongoing. And what we observe, we attributed to the Andreev-bound states that are located inside the niobium gap. So I would like to highlight that this is a promising platform for observing the Majorana zero modes, of course, because it's first of all, it's theoretically possible to see these Majorana zero modes, but of course we have to improve the quality of our devices in order to prepare cleaner devices. And the importance of this is that our approach is an easy one because you can scale it easily, and it's a top-down approach basically. We don't have to grow the nanoribbons. And of course, if you can one day observe them, this final step would be to, next step actually, would be to try to control and braid them for topological qubit structures. These are from the same two papers that I presented before. Using the gates, they would like to braid the Majorana zero modes to obtain a qubit structure. And these qubits will be topologically protected and are building blocks for quantum computation. So I think I will end my talk here. Thank you very much.
Thank you very much for a nice talk and specifically for staying in time. The talk is open for discussions. Are there questions, comments? Maybe I can get started. You mentioned in your second part for the device fabrication that there is some problems with the devices. I think one issue that arises from the gallium FIP is typically that you implant gallium into your device, specifically when you have these very small ribbons. Can you exclude that there is a gallium doping?
So we have also tried this FIB patterning with normal two-dimensional QAHI films, and we can we can measure it so that we can make sure that the helical channel is formed through the nanoribbons, and there is no gallium, there is no defect because of the gallium, that when the nanoribbon is continuous, you can expect the helical channel to be forming, and it should be the chiral edges anyways. It's ballistic and it's dissipationless, and when the helical edge is formed, you expect it to be continuous through the nanoribbon despite the gallium implantation. Yeah.
Okay. Any other questions? Okay, if not, then I think in the interest of time we go on. Thanks very much again.
Yeah. No.
And yes.
Thank you. Thank you very much.